I think, as an organic chemist, is I think you're taught to draw the hydrogen at the back, and then you have your other substituents arranged around it. So you could have your aldehyde, and then your hydrogen, and then your hydroxymethyl, right? You have it arranged like that. Or,
is that supposed to be the bottom?
oh, sorry. Thank you. You could have it arranged in the other orientation. Yeah? Do we remember this from OChem? Vaguely? So the one on the left here, is it R or S? Do we remember how to do this? So what's our highest priority group?
OH, yeah, that's right.
Oxygen is the atom most directly connected, and it has a heavier molecular weight than either of the carbons. So that's our highest. Of these two, what's the next highest priority? Carbonyl. So this one goes clockwise and is R. In this depiction, highest functional group, second highest, third highest. Counterclockwise, this would be the S orientation of the molecule. This reminding everybody? So this system is agreed upon, works for any molecule in the universe, and is the standard. And unfortunately, it was invented in 1956. And glyceraldehyde was discovered in 1896. So we have a different naming standard that predates this nice, universal, helpful one. Yay! Here's my advice to you. If you become a carbohydrate chemist, change this. This is stupid. We've had a better system for 60 years now. I don't know why I'm still learning something and teaching something from the 1890s. But if I don't, you'll be woefully unprepared. So, sorry. Here's how we do it. Instead of R and S, which is standard and makes a whole bunch of sense, we go with how they did it in the 1890s. And here's the idea. If we orient it, instead of putting the hydrogen to the back, if we orient it so that the hydrogen and the OH are facing out at you, and the aldehyde and the hydroxymethyl are pointed away from you, we put the aldehyde at the top. Then we ask, is the OH on the right or the left? If it's on the right, we call it D. If it's on the left, we call it L. We saw this convention before with amino acids briefly. It actually started with carbohydrates and then was exported to amino acids, and it's still done.
Why are we, is it just standard that we always put the carbon or the aldehyde on
top? Yes. You put the carbon with the most oxygen bonds on the top, technically. The most heavily oxidized carbon goes on top. Technically, but usually it's a carbon. So. In this convention again, if the OH is to the right, we call it capital D. If the OH is to the left, we call it capital L. This has nothing to do with the RS system. And in fact, sometimes a D will be R, and other times a D will be S. It also has nothing to do with the rotation of plane polarized light, which is italic or cursive L and D, which are a completely different metric. So there's that. But there is one useful reason, and okay, all joking aside, the reason the D and L nomenclature is retained is it does have one piece of useful info embedded in it. And that's essentially all, asterisk, carbohydrates in your body are the D orientation. Which would be harder to say if we used R and S classification, because some of the sugars in our body are R, some are S. But under this classification system, all of them are D sugars. Notice this is in contrast. If you remember, amino acids are all L amino acids. But all our sugars are D sugars. And so we're going to see that going through, that they're D sugars. As a reminder from many weeks ago with amino acids, I call this kind of projection the visiting relatives you don't like projection. Your arms are out to hug, but you're keeping your distance. Right? The horizontal lines are out, the vertical lines are staying the heck away. I'm obligated to hug you, but you're not kissing me, Grandma. Or whatever. My grandma's nice. Though that's a very common projection, unfortunately, because it gets a lot wrong. Carbons are not 90-degree angles. We're going to deal with it. Those are typically called Fisher projections, after the guy who popularized their use in the 1890s. So 120 some years later, we're still using these bad models, but it's where we're at. And so we're going to see a lot of pictures of carbohydrates drawn in Fisher projections, but I actually don't want you to really love them or like them. I want you to think in better stereochemical terms, because these are very far from reality, and they can lead you down the wrong paths. So I'd much rather in your own brain you put them into something that looks a little more chemically feasible, maybe. If you did forget R versus S, I have a very short tutorial from your book right there. Okay, there. Okay, so here's the deal. If that is our simplest carbohydrate, couldn't we make more complex ones? Couldn't we do more? And the answer is yes, lots and lots more. And we need a way to think about it, to systemize, wow, I'm not using that green again, to systemize it so that we have something to work with. And again, we start with our standard. If we assume that glyceraldehyde is our basement bottom, this is what all carbohydrates come from. And again, this is D-glyceraldehyde, because the OH is oriented to the right side. And you should just forget about L-glyceraldehyde. We're never going to worry about it. So that's the thing. One thing that we could do to introduce more complexity would be to just add more carbons. So if I take glyceraldehyde and I just stick another carbon on, another CH2OH at the bottom, we get a longer molecule. We get a different sugar, a different carbohydrate. But there's a problem here. Because now, where I had one chiral center, I now have two chiral centers. And again, here's where I just want to be completely clear. This is where we're just bumping up against old-fashioned naming. Again, the IUPAC naming system, where we say like 2,3-dihydroxy, was mostly developed in the 1950s in the aftermath of World War II. These were all named before then. Because if we were doing this now, if you were a drug maker and you had discovered this molecule for the first time, you'd say something like RR or RS or SS, right? That would just be the way that you did it. That's how we name molecules. Which can get ridiculous in its own way. If you look at some modern anti-cancer drugs, they're like 2, 3, 4, 5, RS, blah, 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 blah. And that's getting just as bad, right? Like I got lost halfway through, but you know, so the naming is hard. But we would have had something like that where we said, well, this is, you know, carbon 2 is in this chiral configuration. Or we could have even done like 2R, 3R or something. Those would have all made sense. That came about 60 years too late. So here's how they actually decided to name it. You're going to love this. They said the bottom and the top look like glyceraldehyde. If we just had that, that would be glyceraldehyde, and you put something in the middle. Here's why I'm going to say this. Remember we always said we have D sugars? They said this is the one at the bottom that is always D. It's not the one there, it's the one here. It's the one at the bottom that is part of our original structure. So The top and the bottom, that's where we started. You clearly inserted something in the middle. Clearly. And there's two possibilities. You could have had the OH on the other side. So we need a way to tell these two apart. And the way they decided to do that is by coming up with a different unique name for each middle chunk. You put in a middle chunk where there's one carbon with an OH on the right, that gets a name. You put in a middle chunk with one carbon and the OH is on the left, that has an entirely different name. You put in one that has two carbons in the middle chunk, and they're both to the left or to the right. Again, we have our retained glyceraldehyde backbone at the bottom and at the top. We put in this two chunk. That has a unique name. You have the one where it's left and then right. That has a unique name. You have a name where it's both on the left. Unique name. So it kind of sucks. When I was an undergrad, I had to memorize all of the major ones. There's 32. I think that's stupid. We're not going to do it. You're going to memorize like 2 or 3 of the very important ones. But I want to tell you, they thought at the time this was smart. It's the central chemical features, and you get a unique name for what you're putting in the middle. That was the height of nomenclature in the 1890s. We've come a ways since then. But it wasn't meant to be cruel. They just didn't have a better system. And so here's how they named it. I'm going to skip a slide or two to get to it. So skip that guy for a second. Here we go. The first class of sugars we could care about are the ones that contain aldehydes, aldoses. You'll notice at the end of any carbohydrate is this ose, cellulose, sucrose, lactose, fructose. Ose just means it obeys the rules of carbohydrates. Aldoses, we know are 3-carbon one, D-glyceraldehyde. And notice I am only listing one molecule here. Because although we can imagine a state where the OH is on the left, that doesn't occur biologically. So D-glyceraldehyde it is. You need to know D-glyceraldehyde. I'm going to spell it out as loudly as I can so that you don't try to memorize all of these and waste your time. You need to know D-glyceraldehyde. When you put in one new carbon, that is, you slot in one new carbon, that new carbon can have its OH either to the right or the left. If it's to the right, it's a molecule we call erythros, first isolated from red blood cells, hence erythrocytes, erythros. If you have it to the left, it's called threose. Don't learn either of these. They're not useful. They exist, even biologically exist, but we don't care.
Except the names box at the bottom didn't mean that you boxed at the bottom.
Yeah. I'm going to write on the board with my little pen. That's not going to work. When we start to put in 2 carbons in the middle, now we've got 4 possible molecules because we can have right-right or left-right or right-left or left-left. And each of those leads to a unique sugar with a unique name. The only one worth knowing of the 5-carbon aldehydes is ribose. This is what DNA and RNA are made of. And it's pretty easy. It's right, right, right. Right, right, right. Do you know it? Right, 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 right. Okay, right. But they all have different names. And in fact, if you read food packaging a lot, you'll see arabinose added to a lot of foods. It's used as a thickening agent in things like milkshakes. It's like sugar, but when we get there, it's not really sweet. It's not recognized much by your body, and we're not good at digesting it. So it's a good filler if you want to make something thick and gooey, but not super sugary. Arabinose. Xylose occurs somewhat biologically. Lixose, as far as we know, doesn't occur biologically, but it has a name. Lixose. The only one we care about here is ribose, so mark that. And again, if we think of this, when we get to 6 carbons, we effectively are having 3-carbon insertions into our middle piece. And those 3-carbon insertions have 8 possibilities. right, 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 left, right, 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 left, right, right, etc. Many of them are not important to us. In fact, only one matters: glucose. Glucose is the man, and we need to know it, because it's going to occur over and over and over and over again. So, here's my little trick for memorizing glucose if you never have before. It is 6 carbons long. So I put an aldehyde at the top, and I make sure there are 4, 5, 6 carbons. The bottom one's not going to be chiral, so I don't care. It's just going to be some CH2OH. And glucose has fully 4 chiral centers. But the bottom one comes from glyceraldehyde, so I know what that one's going to look like. It's always going to be on the left, or excuse me, on the right. It's D. Glucose is an army marching song to me. Anyone else? Glucose is right, left, right, 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 left, right, right. It's like an army marching song. Right, left, right, right. It'll stick with you. Glucose goes right, then left, then right, and then it has the glyceraldehyde right. Right, left, right. Another way that I learned these when I had to memorize all 32 of the main common ones is 1, 0, 1, 1, if you want to do binary. When they're on the left, it's a 0. When they're on the right, it's a 1. So it's 1011. I don't know. Whatever works for you. I like right, left, right. It's our marching song. Glucose is incredibly common. In Americans, it makes up approximately 45% of our daily caloric intake. In most of the rest of humans, it makes about 30% of our daily caloric intake. Americans eat way too much sugar, like ridiculously, and I'm just as bad, so I'm not like preaching from the pulpit. I'm preaching right down in the trenches with you. I eat way too much sugar. It's a problem. I'm going to get diabetes. Which is a horrible disease and not something I should joke about, but it just rolls off the tongue. So we care about glucose a lot. It turns out, biologically, there are very few 7, 8, 9, 10, etc. carbon sugars. They can exist. In particular, in plants, we see some 7 and 8 carbon sugars, but they're pretty rare, and so we're going to ignore them. 6 is mostly the max. So we could flip to the other side. What about our carbohydrates that have a ketone group? Of the ones that have ketones, there's only one 3-carbon version because it's not chiral. And that's dihydroxyacetone. And you should know dihydroxyacetone. It's worth burning it into your retinas and committing it to memory and having it good to go. When you insert your first carbon into it, we get erythrulose, which you do not need to know. The only reason I want to point it out is at this point, as far as we care as biochemists, there is only one 4-carbon sugar, because we've now introduced our chiral bottom that will always be on the D side. So there's not going to be an L here, we're always going to be D, and so we've now finally got a chiral carbon to define our D state and go with it. And we're just going to keep inserting stuff in between the chiral bottom and the aldehyde, the carbonyl containing top. And so when we do that, we can insert 1, or we could insert 2 for our 5 and 6 carbon ketoses. Of the 5 ones, don't worry about it. Don't think about them. Of the 6 carbons, the only one we want to know is fructose. I'm going to give you a trick to drawing fructose in just a second. But I just want to point out, of the 6 carbon ketone containing sugars, fructose is the only one that really occurs biologically a ton. Tagatose happens in some cacti-like plants, succulents, there's the word. Tagatose occurs in some succulents. Sorbose occurs in a lot of molds. Bacteria and molds use sorbose. A lot of multicellular life doesn't. And psychose doesn't occur at all naturally as far as I know, but man, I kind of want it.